Today, as I promised previously, that we are going to discuss projectile motion. That is motion in 2 dimensions. And so projectile motion is part of the discussion that we're going to look at today. Basically, we will develop concepts which will enable us to tackle any question in projectile motion. And so here we go. What is projectile motion? Basically, projectile motion is a topic to be discussed today. So when an object is launched in air with an initial velocity in an arbitrary direction, we say that that object has been projected. And therefore, the object will move in the vertical plane and will be acted upon by the gravitational acceleration. So here we see that there is an effect of acceleration due to gravity. And so the path that the projectile pass through is known as the trajectory. So because we normally ignore air resistance as well as acceleration in the y plane is considered to be due to acceleration due to gravity, and therefore we say that acceleration should always be as a result of acceleration due to gravity. While in the x plane, acceleration is 0. And so this is the diagram which shows the preliminary depiction of how a projectile can move. Well, you notice that here we have the y plane here and the x plane. And so if we launched a projectile at an angle theta, it will move through this path until it finds itself again to the ground at the same height. And so this is the path of the projectile as it moves through air. And this is what we called trajectory. And so the projectile will eventually reach its highest point. And this is the highest point which we have indicated by H here before it starts coming down. And then the distance that the projectile will take from the point of launch to the point where it comes back to the ground is known as the range. And therefore we have shown it as R here. And so in projectile motion, to enable us to calculate the time that it will take for the projectile to move from the point of launch up to the time when it lands to the other side, we have to break this in two components because, as we said, it is a two-dimensional depiction. So we have to break this velocity into the x and y component. So let's assume that at time t is equal to 0, the projectile leaves the origin at an angle indicated here, which is theta. We note that the x component of the velocity will be this velocity, which will be the hypotenuse here. And then if you draw some triangle here, you'll notice that this point here will be adjacent. This angle here, the angle here will be adjacent to this side. And therefore, you can use the cosine law. And therefore, the velocity component in the x-axis, that's why we called it Vox is equal to Vo cos theta. This is the velocity, the actual velocity. And then this one with an x is the velocity in the y component, I mean the x component. And in the y component, also we can do the same. It means that here we have to look at what is opposite to this angle, and therefore we can use the sine law. We can say the velocity component in the y direction is equal to velocity, this actual velocity sine theta. It means that we have broken this in two components, the velocity in two components. And so if we want to find the displacement, that is the distance that the projectile is going to pass through in the x-plane, as usual, you remember when we were at the high school, you could have this, you are very familiar to this equation for displacement, where we said S is equal to initial velocity times time plus half acceleration. In our case, this is acceleration due to gravity, and then t squared. So you note that as we indicated earlier, acceleration due to gravity in the x-plane is actually 0. And therefore, we can be able to show that this g disappears here. And so in this equation, you see that the x is equal to x0 meaning that this is the starting point, and this is the point at which the particle is going to land. And then we have the component. As you know, this is the initial velocity, which we broke into component, which we said Vx0, you remember, as we had to show it here. So, times time. And the Vxo, you remember that we can show it as Vo cos theta when we broke it into components times the time. And so we note that here the displacement has no acceleration in the x component. We go ahead again and find the displacement of the projectile in the y plane. You notice that the usual equation for displacement is shown here to enable us to fully understand what is going on to the projectile. And so we said the displacement is equal to initial velocity times time plus half times gravitational acceleration times time squared. And so here we know that the y component is affected by the acceleration due to gravity. Therefore, we can say displacement is equal to y, where the particle will be, and this is the y, where the particle is starting from, and then we have the initial velocity times time, the y component, minus, since this is moving against gravity, you know, this projectile is moving upwards. So that's why there's a minus here, and then g, which is gravitation due to acceleration, t squared. And then we can replace the VYO as with the component. Okay, component velocity. And this gives us actually the displacement of the particle in the y plane. So we can similarly find the velocity of the projectile in the y plane. To find the projectile in the y plane, as we indicated, if you have a position vector, it means that you have to differentiate that position vector to enable you to find the velocity of the particle or the projectile. So this above here was our displacement, and if we differentiate it with respect to time, you note that we get velocity in the x component will be equal to velocity initial cos theta. The time has disappeared because we have differentiated the position vector or the position expression. Similarly, for us to enable us to get the velocity of the projectile in the y component, you come to the displacement expression and differentiate it with respect to time. And you note that if we differentiate y here, position vector, it will be 0, and then the initial sine theta times t. When you differentiate this one, the time will disappear. And then when you differentiate t squared, also here we are going to remain with the minus gt. And so this is the velocity of the projectile in the y plane. Now, let's go now and look at using these expressions that we have come up with and look at the time for the projectile to move up and come back to the same position. In other words, we are saying, what time does it take for the projectile to move from this point here, the initial point, up to the point when it comes back to the ground again? And so we note that the time can be calculated by ensuring that the y, you remember, should be equal to y initial, meaning that the projectile starts from a certain point and comes back to the same point. And so you note that our expression here for y will be 0. And then when we express t with respect to what is remaining here, find that our time will be equal to 2 v initial sine theta over g. So this is an expression each time you are asked to find the time of the flight for the object. For example, for the complete movement of the particle from one point to another until it lands. If it lands back to the same point, it means that we have to use this expression of time. Now, as we indicated the area, we said we can as well find the distance that the projectile covers from the point of launch up to the time when it reaches its destination. And this is the distance which we called the range. So the expression for calculating the range is actually as well derived from the expression, because expression for the distance that is covered in the x plane. Because you remember, we are measuring the distance in the x plane from this point up to this point. And therefore, even the expression we're going to use is an expression for the x plane. And therefore, using our usual equation, where we are saying speed is equal to distance over time, you notice that this would be the displacement, and this one is the velocity component, and then this is the time. And so the range would be equal to, this is the range actually you are measuring the movement of the particle from x0, this is the point x0, to the point x. And therefore, for you to find this distance from x0 to x, you have to subtract x minus x0, which gives us the range. And therefore, we can ably calculate the range by saying x minus x0 is equal to the velocity component times the time. And you notice that for the complete flight of the object, we found the time as 2 v initial sine theta over time. And therefore, we can replace where there is time here, we can replace the time. We can replace this expression, and therefore, our range, after making these rearrangements, you'll find that we are going to have 2 v initial squared cos theta sine theta over acceleration due to gravity. Now, according to basic trigonometry, you notice that 2 cos theta sine theta is equal to sine 2 theta. And therefore, that's why I've seen that the 2 cos theta sine theta has disappeared, has been replaced by sine 2 theta here. Because this is merely using trigonometric identities. An expression for a trigonometric identity, which is 2 cos theta sine theta is the same as sine 2 theta. And therefore, for the range, this is the expression that we are going to use to solve all projectile motion expressions. Now, how do we find the time at the maximum height? If you want to find, we launch a projectile from this point here, what time is it going to take to reach the highest point here? This is what we are talking about here. And so, this is a simple expression as well as the simple understanding that at that point, the velocity, remember, we had to differentiate the position vector for y, and therefore here we are interested in the movement of the particle in the y plane. At the highest point, just momentarily before the particle starts going down, its velocity is 0. And therefore, on the expression for velocity, remember here we said velocity in the y component is equal to v initial sine theta minus gt. And so all we are going to do here is to ensure that this comes 0 and make t the subject of the formula. And you will note that the time is equal to v initial sine theta over g, which is basically half of the time for the complete flight. Remember, we found time here to be 2v initial sine theta over g. And this one time has just been halved. Now, what about the maximum height? What is the maximum height that the projectile is going to move from the time of launch up to this highest point? We need to find that one. And therefore, it is again a simple expression that we're going to use. You remember we came up with an expression for displacement in the y plane. And so if we say a particle is moving from this point here, which is y0, meaning that this is the initial y, and it goes to some point there, which is the highest point, which is y. To enable us to calculate this distance, which is the highest distance from this point up to that point, which is similar to this point up to that point, it means that we have to subtract y minus y0. And therefore, you note that when we go to our expression here for calculating the highest point, we will say y minus y0 is equal to the highest point. And this is the expression for the displacement of a particle in the y plane. And merely here, it means that all we need to do now is to substitute the time. You notice that we calculated the time for the highest point, the time it will take for the particle to move from the point of launch to the highest point, and which we found to be v0 sine theta over g. So we substitute it here where there is time. Similarly here, we square that same expression. v0 sine theta over g. We square it. And so what you are going to get is half v initial squared sine squared theta over g. It means that we have found the expression for the highest point for the projectile. So in the next lesson, we will now look at how we can apply these basic concepts to enable us to actually solve several projectile motion questions. I hope you have enjoyed this explanation, which has given us the basic concepts of projectile motion or motion in 2 dimensions. Remember, not to forget to subscribe to my YouTube so that you can learn more of these basic concepts in physics. I thank you.